Hello students, welcome back. In the previous video we talked about the implicit differentiation technique and also a bit of theory. We went through one example which was rather typical. Not easy, but typical. Let's resume our discussion with a couple of simple examples and then a hard one. Okay, let's go to this example. We saw this before as a motivating example. We take the derivative of x squared, x squared over here, and that's 2x, alright, over 9, and then derivative of y squared, that's 2y over 4, and derivative of constant is 0, so we have this. 2/9 x plus, after simplification, 1/2 y is equal to 0. And then what do we do now? Is there something missing? Is everything okay? Well, I hope everybody recognized something here. Something is missing, and that something is the most important factor. As a matter of fact, we are looking for y prime in this problem, and where is y prime? That was missing. The most important factor was missing here. I'm afraid, however, this was very typical mistake that I usually see almost every semester, as a matter of fact. Whenever you take the derivative with respect to y prime pops out, and this is so important that I'm highlighting in different color. And then eventually you're looking for what is that y prime, and basically that is implicit differentiation. So if you don't have y prime popping out, or incomplete, some y prime popped out and some you missed, you're not going to get your answer. Let's kill this, and then let me show you the full solution here. It's simple. Take the derivative implicitly and solve for y prime. Because there's only one y term, only one y prime popped out, and solution was very, very simple. Here is mathematical verification, and what do you get? Negative 4x over 9y of x. That's it. By the way, here is the picture. We all saw the picture before in the previous video, but here it is anyway. Next example, Descartes-Folium, a little bit harder example. This time we have two y terms here, y cubed here, and then 2xy there. So you have to expect two y primes popping out, and consequently you have to pull all those y prime terms in one side, everything else to the other side, and so for y prime. How does it go? Well, here we have y prime by chain rule, and then this one we have a product rule, 2x times y, and the implicit differentiation goes like this. Just for a change, I'm using dy over dx notation here, highlighted in blue. The same technique was used, as a matter of fact. By chain rule, we have y prime popping out here, and you use product rule, and then in the end y prime popped out for the function y. And then we take all the dy over dx terms in one side, everything else to the other side, factor out this dy over dx, and then finally solve for dy over dx. Exactly the same kind of thing. Here is mathematical verification. Oh, let me get that solution, symbolic solution again. We have 2y minus 3x squared over 3y squared minus 2x. Here what do we have? 3x squared minus 2y over 2x minus 3y squared. Are they the same? Yes, they are. All you have to do is multiply -1 to both numerator and denominator, and you're going to get one from the other. That's quite typical with mathematical computation. It may not match precisely with your computation, but it's going to be the equivalent form if you did it right. By the way, this is the picture, Descartes-Folium, we all saw before in the previous video. Now let's go over to a harder example. We went through two simple examples, one hard one. Let's talk about the second derivative. Let's resume from here we take the derivative implicitly, and what do we get? Taking the derivative, and then solving for y prime, we got that. That's something we already discussed. So this is where we resume in the next example. All right. We got that. And then we take the derivative once again, this time using the quotient rule. Wow. And this is what we get. You have u prime v minus u v prime in numerator, and then you have v squared. So denominator squared, that's easy. And when you take the derivative of the numerator, please note the implicit differentiation. So y prime popped out appropriately. And again, in this part, the derivative of the denominator, again y primes popped out appropriately. And what is that y prime? It's right here. So if you plug those in, you get this solution here. Wow. And if you want to find out y prime value, all you have to do is appropriate x and y values to this expression, and you're going to get the second derivative y double prime. But then again, oh my, is this really feasible? Well, if your problem explicitly asks you to find out y double prime, second derivative symbolically, and then find out its numerical value for given x and y value, you have no other choice. You have to do this. You have to find out y double prime first symbolically. And sometimes you may get away with just this if your problem gave you symbolic solution and then x value, y value, and y prime value. In that case, you can get away with this, but then again, it's again pretty bad. This is general solution. But then again, frequently, you're not asked to find out the symbolic expression of the second derivative, just numerical value. In that case, there is a way to get around this quotient rule and horrendous computation. And let's discuss that. Let's begin with a little bit simpler example than the kind of example we went through before. And this is simpler because powers are smaller. All right. First step is to take the implicit differentiation. No, excuse me. Y value was not given. We only have x equals to 1, so finding out y value is the first thing you should do. So here we go. Find y value, and this is not y prime, so we don't need derivative. Find y value from x equals to 1. How do you do that? Plug in x equals 1 here, plug in x equals 1 there, and you can solve for y. Luckily, it's not too difficult, and even better, even more luckily, we only have one solution, y equals to 0. Out of sheer luck, as a matter of fact, we could have multiple y values. In that case, we have to consider all the y values in the next steps, but luckily we didn't have to do that. Plug in x equals to 1, and then after some simplifications, we end up with y cubed plus y equal to 0, and that has only one real solution, because y squared plus 1, this never becomes 0, it's always positive. See the solution? Okay, now that we got x equals to 1, generating y equal to 0, you can go ahead and take the derivative here implicitly to find out y prime. How do you do that? Take the derivative implicitly, yes, we have to do that, and then you can plug in x equals to 1 and also y equals to 0. Here we go. Take the derivative implicitly. Yes, derivative of x cubed is 3x squared. That's easy. Derivative of this xy by product rule. Here we go. Derivative of first function plus first function times the derivative of the second function. We get this y prime. And then here, derivative of this y cubed, 3y squared, and then y prime popped out. Don't forget y primes. Now we are looking for y primes. x is equal to 1 as the problem gave you, and y is equal to 0 as we found out earlier. We're going to plug all those in, and that's going to give me y prime value. Here we go. You see, plugging in all those values, x is equal to 1, y equal to 0, and simplified. Because of this 0, our problem became very, very simple. This part didn't do anything, just went away. And then we have 3 plus y prime is equal to 0, y prime is equal to negative 3. So what do we have? X equal to 1, y equal to 0, and y prime is negative 3. What are we looking for? We are looking for the second derivative, and starting from the original x, original y, and then we got y prime, gradually we are getting closer and closer and closer. Now, are we looking for y double prime? Alright, we have to take the derivative once again. You see, from here, implicit differentiation, we take the derivative once again implicitly. We do not have to solve for y prime and go with this terrible quotient rule. Just take the derivative once again implicitly. Just be careful and follow the same process. Here's the answer. Let's see how that works. 3x squared becoming 6x. Good? Good. Y, if you take the derivative by y, that's 1, but y prime popped out, so we have y prime. Good? Now, quotient rule, x times y prime. Oh, excuse me, did I say quotient rule? It's product rule, excuse me. X times y prime, apply the product rule. The derivative of the first function times the second function, and first function times the derivative of the second function. 1 times y prime, and then x times y double prime. You see? The same implicit differentiation technique. Now, another product rule here. I almost said quotient rule once again. Another product rule here. The derivative of the first function is 6y, and then second function, oh no, the derivative of the first function is not 6y, 6y and then y prime. And then the second function, and then the first function, 3y squared, times the second function, y double prime. So it's a little bit tricky, but it's the same implicit differentiation technique. Now let's go to the final step. Originally we got x equals 1 and we found out y is 0, y equals to 0. X is given as 1 and we found out y is equal to 0. And then through implicit differentiation we found out y prime is negative 3. We're going to put all those here. X is 1, y is 0, y prime is negative 3, and simplify. Thanks heavily to y equal to 0, we get something simpler. You see, plug in y equal to 0, all this part just drops out because you're multiplying by 0. So you don't have to worry anything about this part. What do we get? 6, oh, typo. Negative 3 minus 3 is not negative 7. Okay, that's right. Okay, here, 6 minus 3, another minus 3, plus y double prime, and then all this part is 0. So we get y prime is equal to 0. That is the answer here. How did you think this problem? Really hard? Okay, I don't blame you. This is a kind of problem that has much less than 50-50 chance of showing up in the exam. Much less, I said. Not just about 50-50, but much less. But then again, the probability is not 0, you see. There's some chance I can pick up and then write this as A-level problem.